All right. Today we're going to look at lesson 6, which is titled Factoring Polynomials Using the Rational Root Zero Theorem. So we have thus far looked at solving polynomials by factoring, with special cases, GCF, difference in sum of two cubes, quadratic form, grouping, things like that. But what do we do if it's not groupable, it's not one of those special patterns, and we don't know one of the zeros already? So that's what we're going to be looking at today. So let's start. I want you to consider a quadratic equation with roots of 2 and 3. What would be the factors of this equation? That's right. Now, it would have some a in front of it, wouldn't it? That we don't know about. But let's not worry about that right now. What happened if I expanded this out? What would I get? I get x squared, like minus 5x and minus 6, right? So my question is, how do the roots relate to the constant in the constant term in the equation? What I mean by that is this term right here. So how do the roots relate to that? They multiply together to make it, don't they? Right? And let's go generally. Let's say I'll say that they have to divide that, don't they? They need to divide 6. But for here we could say 2 times 3 is equal to 6. Now it turns out that I did not do this correctly, because this should be a plus 6. Excuse me about that. I wouldn't have already got that, but it turns out these could have been -2 and -3, something like that. So which made me think of it. So we don't necessarily know the signs of them at this point when we look at this, but we know that they have to multiply to 6, right? All right, let's consider the quadratic equation with roots of -1/2 and 3/4. What would be the factors? Okay, 2x plus 1 and... Okay, so that one was kind of tough, right? That one was trickier. You had to think, well, this number on the bottom here had to be what I would divide by in front of the 2. So, all right, let's expand this out. I would get 8x squared minus 6x plus 4x is -2x and minus 3. All right, did I do that correctly this time, since I failed last time? Did I do it correctly? Yeah, I think so. All right, so my question now is, how do the numerators of the roots relate to the constant? Remember, the constant is right here. How do they relate to it? Yeah, they multiply together. So like 1 times 3, or in this case, a -1 times 3. And like I was saying earlier, we wouldn't know if it was like 1 and -3, or we'd have to do more work. But we know that they multiplied together to get that. But what about the denominators? What do they relate to? The leading coefficient is here. That's the leading coefficient. Yeah, 2 times 4 is 8. So do you see this relationship between the roots, that the numerators of them multiply the constants? Now, and I would argue that these roots here of 2 and 3 were 2 over 1 and 3 over 1. Okay, so we could talk about numerators here. The numerators multiplied to the constant, and the denominators multiplied to the leading coefficient. Same thing here. Denominators multiplied to here. Excuse me, numerators multiplied to here, denominators multiplied to here. I mean, that's been how you factor it. If I gave you this equation and said, hey, try and factor this, you're going to start looking at numbers that multiply to this, at numbers that multiply to that, right? Well, it turns out this pattern continues to higher degree polynomials. So in general, the rational roots of a quadratic equation ax squared plus bx plus c must be of the form p over q, where p divides c and q divides a. Okay, that's a mathy kind of way of saying this. What we're saying is that any root to that equation, p over q, must be in the form where the numerator goes into the constant and the denominator goes in evenly to the leading coefficient. That's what the word divides mean. The word divides means divides it evenly with no remainder. Okay. Consider a polynomial equation with roots of -2, 3, and 1/2. Let's go over what would be the factors of this polynomial. Well, they'd be x plus 2, x minus 3, and this would be 2x minus 1, so that you get a 1/2. So let's expand this polynomial equation. Well, I need to do it at a couple different steps. So the first step, I'll multiply this out and get x squared minus x minus 6. Then I'll multiply that times 2x minus 1, giving me 2x cubed minus 2x squared minus 12x. Then I'll multiply by the -1, negative x squared plus x plus 6. So that gives me 2x cubed minus 3x squared minus 13x plus 6. How do the numerators or the roots relate to the constant term of the polynomial? 2 times 3 times 1 is 6. And I mentioned earlier that we don't really know about the signs so much. Yeah, we don't really, it turns out this multiplied to these ended up being a positive 6, but one of these were negative. Don't worry about that. The key, though, is that 2, 3, and 1 multiply to 6. Okay? How do the denominators of the roots relate to the leading coefficient? 1 times 2 is equal to 2. So we see that in larger polynomials, this same thing is happening, that the roots have to be some fraction where the numerator evenly divides the constant, the term at the end, and the denominators divide the term at the beginning. So in general, the rational roots of some cubic equation, ax cubed plus bx squared plus cx plus d equals 0, must be of the form p over q, where p divides d and q divides a. To finish discussion, we must generalize a polynomial and introduce a new symbol. All right, so this is the definition of a polynomial in general. Notice that I no longer use a, b, c, and d, because a polynomial can have more than 26 terms, and I run out of letters pretty quick, don't I? So I'm going to describe a polynomial as a sub n, where the subscript is just telling you which one I'm talking about, and it corresponds to the exponent. So if this is x to the 7, I call that a sub 7. Okay? So it's a little bit confusing notation. I just introduce it here just to get you used to looking at it. So this is a polynomial of x. I'm going to say that a divides b if and only if b equals a times some k for some k in the integers. In other words, a divides b means that b divided by a has no remainder. So for example, 2 divides 6 is true, but 2 divides 5 is false. Okay? So that's a new operator for you. Again, this is not of great importance that you learn all this right now, but anytime I get a chance to teach you a little bit of formal math definitions and operators, I will take that opportunity. So now we can talk about a really cool theorem using some cool mathy terms. The rational root theorem says that any rational roots to this equation, you look at that and your typical person says, oh my gosh, it looks like math threw up. But you look at that and you say, I know that's just a polynomial. Okay? So any roots to this polynomial must be of a form something over something where p divides a sub 0. What's a sub 0? The constant. And q divides a sub n. So any rational root of any polynomial has to be of a form where the top goes into the last number, the bottom goes into the first number. Okay? There's a related theorem for polynomial functions. They just changed the word root to 0. Okay? There's a key word, though, in this theorem. It's not the root theorem, is it? It's not the, remember, root just means solution to an equation. I prefer the term 0. I really do. So it's not saying the 0 theorem. It's saying the rational 0 theorem. They have to be rational. So if your 0 is the square root of 3, it doesn't work because the square root of 3 can't be made into a fraction. So I can't talk about its numerator or its denominator. It has to be only its rational zeros. Okay? All right. But that's good because in this class, there will always be at least one rational 0 to our polynomials. All right. Let's do one together. Given the following polynomial function, x cubed minus 7x minus 6, what is the degree of this polynomial? 3. Is the polynomial factorable by grouping? It is. If you think it is, give it a try. Well, for one thing, everything we've grouped has always had how many terms? 4 terms. Because we've got to be able to group them in 2 and 2, right? So this is already not looking too good for grouping. And in fact, I wouldn't be able to make 2 equal size groups. So no. We're going to say it's not groupable. And we've shown that you have to have a constant ratio between the first 2 terms for that to be possible. What about, is it in quadratic form? We've seen this before where if it's 3 terms, maybe you can factor it just like a quadratic. Also no, because this would have to be like a 4 and then a 2 and then a 0, right? This is 3, 1, 0. This has to be like twice as big as that. It doesn't. So no. So it's not in quadratic form either. All right. All right, we're going to use the rational 0 theorem to generate a list of all the possible rational zeros of f. This problem's not too hard. Just like if I gave you like an x squared problem to factor, if there's no number in front of the x squared, you're like, oh, this is easy to factor, right? Same thing here. It's a lot less difficult because I already know all my rational zeros have to be integers. Because the denominator has to go into a 1. And what's the only integer that divides 1? 1. So we just need to think of all the numbers that divide 6. Well, the first number that divides 6 that comes to my mind is the number 1. What's the next number you can think of that divides 6? What else? What else? All right, and as I told you earlier, though, we really don't know the sign. So what we're going to say is we're going to say plus or minus. Okay, because we would say that negative 3 divides positive 6 and positive 3 divides negative 6. They both divide because they have no remainder. So we have a total of 8 different possible rational zeros. However, 6 cubed is 216. 1 cubed is 1. Which one of those numbers is closer to 0? The chances that a number is a 0 gets less and less likely as we move this way unless these coefficients here become very, very big. Okay? So I'm always going to start with the smaller magnitude numbers. Okay? So here's what we're going to do. We're going to do synthetic division. This f of x can be written as 1, 0, negative 7, negative 6. I could use long division as well if I wanted, right? But I'll use synthetic. The number that I put there is the opposite of what I'm dividing by. So I'm going to try dividing by x minus 1. Okay? So what I put there is 1. But we learned from the remainder theorem, this is actually the same as just evaluating at 1. So if I get a 0 here, then I know 1 is a 0. Okay? Where did I get that 1 from? It's one of my 8 choices. Okay, bring this number straight down. Multiply. Add. Multiply. Add. Multiply. Add. It didn't work. That's okay. We didn't fail, did we? We eliminated an answer choice. We have an 8-question multiple choice test here, and we just eliminated an answer choice. Let's try another one. What's another number I could try? I tried positive 1. Okay. So, the chances that it was 1 or negative 1 are pretty darn good, actually. I probably had to think pretty hard to come up with an example problem where 1 didn't work. Because I want you to see me fail. Because I didn't fail. I guessed and test. Right? Okay. So, it turns out that there were a couple other choices that would have worked as well. All right, so what do I now know? Well, I know from the factor 0 theorem. What's the factor 0 theorem? Factor 0 theorem says, hey, you found a 0? Guess what? Its buddy is a factor. Right? So, f of x, we know that negative 1 is a 0, so x plus 1 is a factor. Also, I could just be using the idea that we know the definition of a factor is that it has a remainder of 0. We were dividing by x plus 1. So, f of x is equal to x plus 1 times x squared minus x minus 6. That's what I get from right there. Okay? How do I know? I divided by x plus 1, and I got that as a result with no remainder. So those two things must multiply to that. Multiply it out if you don't believe me. Okay. Now, can we factor this? Because it's a quadratic. We can use basic factoring techniques from there. All right, it's going to factor as x minus 3 and x plus 2. So now, let's find the zeros. Negative 1, 3, and negative 2. Let's check by graphing it. Do we really need to check by graphing it? Not necessarily, except for the fact that polynomials look cool when you graph them. So it would make sense to do that. So our equation was like x cubed minus something. What was it? All right. This is what I got. Negative 2, negative 1, and 3. Isn't that cool? Yes, if you have the right kind of display that's adaptive. Oh, those are the minimums. We can't do that yet. We're not in calculus. So there we go. Yeah, you'll notice these extra dots are telling us these important points here. Calculus tells you how to find that point and that point. So something to look forward to. Okay, give it a try. Do practice 6.1. All right, let's go over practice 6.1. What is the degree of the polynomial? 3. Is this polynomial factorable by grouping? Well, maybe you think it is because it's got 4 terms, but it turns out it's not. The ratio would have to be the same from here to here as here to here. If you try and group it, what you end up getting is x minus 6 in one group and x minus 30 in the other. So it doesn't work. Like this, the ratio from here to here has to be the same as from here to here. Like, so if this was like 1 to 6, and then like, so let's say this one was like 2 to 12, then that would work. Or at least it's worth trying if it looks close to that. All right, so we're going to say no, neither. Well, let's use the rational zero theorem to generate a list of the possibilities, okay? So how about plus or minus 1, plus or minus 2, plus or minus, what else goes in the 30? 3? Mm-hmm. 10. Wow, that's a lot. That is a lot. I'm surprised that many numbers go in the 30, frankly. And considering that there's only 2 numbers that go in the 31. So that's 16 different numbers. But, 30 cubed is a big number, right? That's a big number. So it's probably somewhere over here. Let's try 1. Well, not with that attitude.
I mean, with a good attitude, it's not going to make it the right answer.
The answer is not 1.
It's not 3. It's not 5 either. It's not 3. It's not negative 3.
I'm going to try 2.
Just keeps going up in the numbers.
We'll get there eventually.
Okay. Now he's doing it on his calculator.
I am not. Well, which one y'all want to try next?
15.
I don't want to try 15 until I've tried everything before.
No.
Peyton, what did you say?
I'm thinking negative 2 has
Some
some potential.
potential?
Yeah.
All right.
Did you do negative 2? Yes. Did it work? Okay. Hey, why don't you start with this?
Negative 2. So that was negative 8, 16, 15, negative 30. Oh, it worked! So transplant that right there. So I'm going to rewrite f of x. X plus 2. So negative 2 is a 0. Now check it out. This is the result. The remainder was 0. This is x squared minus 8x plus 15. We were cubed. We go down by 1 to squared. So that tells me this is x squared minus 8x plus 15. This is a quadratic. I'm not guaranteed to be able to factor it, but if I can't, I can always use the quadratic formula. But let's keep trying to factor. State the zeros are negative 2, 5, and 3. So we could have tried 5 earlier, and we could have tried 3. I think I heard multiple people yell out that neither 5 nor 3 work, so you may want to check the... Okay. All right, let's use a graphing utility with the following window settings to help us sketch the graph. So let's do that on Desmos. And then we can sketch the graph. So what's it say should be my window? So what's it say is my x-min? It says negative 4. Can y'all read this out for me, please? Negative 4. What's the x max? Okay. And the step is by 1, probably. And what's the y min? And the y max? -10 on the y min. That's not low enough to see. Oh, that's a shame. By 5. Well, dang. Oh, I know why. Because I haven't changed the equation yet. What's the equation? Aha, does fit. However, I am, famous for giving people graphs that don't fit. So there we go at 3, at 5, and at -2. Notice this would be pretty easy to graph yourself if you had a way to find these points here and here, but you don't because you're not in calculus class. I know, but no, you have to wait. When you are ready, Grasshopper. Okay. All right, so the following problems will include a mix of older type problems that can be solved without guessing and testing rational roots, with our newer problems that do require it. So let's start with the first one. So you're confronted with solving this. The truth is, I can always start guessing rational roots and dividing. But that's kind of slow, right? I mean, that's just blind, stupid guessing. If there's a better way, let's use it. So I look at that and I see 3 terms. So I start thinking, oh, maybe it's quadratic form. 4 is twice 2. The exponent here is twice the exponent here, and then there's no exponent there. So this is quadratic form. So we can factor it as if it were like x squared. But instead of x and x, I do x squared and x squared, because x squared times x squared makes x to the 4th. Then I need numbers that multiply to 50 and add to 27. Well, that's 25 and 2, both of them negative. This is a difference of 2 squares, so keep factoring it. Now, x squared minus 2 is not factorable because it's not a difference of 2 squares, because the 2 is not a perfect square. Now, I can set each factor equal to 0, and we're used to skipping this part here, but I just want to show it that I'm not stuck because I can solve each one of those equations. This one, of course, is 5, and this one, of course, is -5, but on this one here, I can use square roots because I have a quadratic equation where I have an x squared, but I don't have an x term. So I'll simply add 2 to both sides and take the square root of both sides, but what do I need when I take a square root of both sides? There we go. So the solutions to this equation, or roots if you like to be formal, are 5, -5, the square root of 2, and negative the square root of 2.
So can you only do the very first part is
Quadratic form. Or, we could use, or some other special case. It could be a difference of 2 squares or something. All right, let's take a look at the next one. This is a 4-term cubic polynomial. So that's when we say, ooh, I hope it's groupable. And I look at it and I say 2 to 9, that's not the same as the ratio from 6 to 1. It is not going to be groupable. So we're going to make a list of possible rational zeros, or possible rational roots, if you will. Okay, so the rational roots have to be of form P over Q, where P divides 1 and Q divides 2. So what I want you to do is to list all the factors of this number. There they are. When there's a number over here, though, you need to list all the factors of this number again over each one of the numbers that divides 2. That is 1 and 2. I've already done the 1, there's the 2. If this was like a 4, I'd have to do 1, 2, and 4. I'd have to do plus or minus 1 over 4. And if this was like a 6, I'd have to list each one of them several times. So you can see how they get quite a bit when there's a number here. So let's start doing our zeros. 2, -9, 6, -1. I don't know if it works, but I really want to try the 1/2 because I want to share with you something that will help you. Nobody likes fractions, right? But Well, they're better than decimals. But the thing is, when you synthetic divide, if you ever get a fraction down here below the basement, stop. That number doesn't work. Okay? You don't need to sit there and start adding fractions. No. So, bring this down. And I say down here, any fraction up here, too, in this middle column. No. Once you get a fraction, it's over. So, if this works, these should all magically work out to be okay. So, when you multiply 1/2 times 2, divide by the bottom. 2 divided by 2 is 1. So, put it there. That makes this -8. 8 divided by 2 is -4. That makes that a 2. 2 divided by 2 is 1. It worked. So we can refactor this as x minus 1/2. And then that's 2x squared minus 8x plus 2. Now you might be tempted to try and do something clever where you say, oh, 1/2, that means this is 2x minus 1. Don't. But instead, I'm going to show you what you can do. Do you notice that this has a GCF? Anytime I synthetically divide or real divide, long divide with a fraction, you're always going to have a GCF here. I can pull it out. I'll pull out the 2. Now, look at that 2. Then now I can distribute it over here, making it 2x minus 1. Now, that step is purely for style. It's not necessary. You can leave it as x minus 1/2 times 2. You can put the 2 right out here in front. Doesn't matter. But isn't that kind of cool that it'll always work out that way? That's not factorable. Let's use a quadratic formula. So my zeros are 1/2, because that's the 0 there, but we already knew it. Or my root, in this case, it's an equation. Then the quadratic formula here. So I'm not able to solve this by factoring. I could solve that one by factoring, but not that one. Okay? So I'm going to solve. What I'm doing is I'm setting each one of these things equal to 0. Okay? Setting each of them equal to 0. That one's easy. That one requires a quadratic formula. So 4 plus or minus the square root of -4 squared minus 4 times 1 all over 2 times 1. So that's going to end up being the square root of 12, which is 2 root 3. So this is 4 plus or minus 2 root 3 over 2, or 2 plus or minus the square root of 3. Okay, kind of running out of room here. So my roots are 1/2. 2 plus the square root of 3 and 2 minus the square root of 3. Remarkably enough, there was only one rational root, and I got it on the first try. Well, there were only 4 choices. I guess it's not that amazing. Okay? Let's take a look at C. Okay, I got a 4-term cubic. What do I want to try first? See if it's groupable. 1 to 3, 1 to -3, 4 to -12. This times -3, this times... Yeah, it's perfect, y'all. So we're going to group it. Yes, we could do what we did and we would get the right answer. But this is faster. All right, we'll factor out an x squared on the first group. And I'll factor out a 4 on the next group. Okay, and this gives me x minus 3 that's in common, and then x squared plus 4. I can set x minus 3 equal to 0, and I can set x squared plus 4 equal to 0. Because that's not a difference of 2 squares, because it's not a minus. This gives me 3. What about this one? Yeah, they're imaginary. Square root of -4, that's not real. And we're not doing imaginary numbers right now. It says real roots in the instructions. So the only solution here is 3. Okay. I think all we're going to do left is go ahead and try 3 problems on your own. Okay? Remember to try the old techniques we've done first if you can. And if you can't, try guessing rational roots. All right, let's see how we did. Is this groupable? No. So my possible rational roots list is plus or minus. All the numbers that divide 8 are 1, 2, 4, and 8. But that's just assuming the denominator is 1. But because I have a 3 here, the denominator could be 1 or even 3. So I'm just going to repeat this list. Okay, and you want to be careful. Sometimes when you're dividing here, you actually get some numbers that repeat from earlier. Didn't happen in this case, but you can cross them out sometimes. All right, let's try dividing. I'm going to start with let's see here. If I did a 1, let's see here, I'd be like, yeah, I'm not feeling the 1, but what about the -1? That would give me. Yeah, I'm not feeling that either. I'm going to try 2. Oh, I'm hearing 1 does work. Okay. Well, I was just giving it a glance at what I, kind of felt like would work. But sometimes my intuition is wrong, and it is definitely wrong here. Okay, cool. No. You did well. You did well. So that's the thing. Sometimes you can look at it and say, 1 didn't look good. I was just picking 1 to start with. And I'm glad you stopped me because that was definitely the right one. Yeah, that's true. All right, I'm going to factor this as 3x, because this looks factorable. Let me double check. 3 times 8 is 24. Something that subtracts to 2 that multiplies to 24. Yeah, 6 and 4. 6 and 4, yeah. So that would be positive 6x. And then if I do minus 4x, I get the 2 in the middle. So, all right. So it looks like our solutions are 1. Can we do this in our head? Add the 4, divide by 3, and -2. X equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. So that's 4 minus, that's a time sign, minus, this could be a plus here. So 12 times 8 is, see, 12 times 8 is 96. Plus 4 is 100. So this is -2 plus or minus the square root of 100 over 6. Square root of 100 is 10. So I have -2 plus 10 over 6. So that gives me 8 over 6, which is 4 over 3. And that gives me -2. All right, let's try the next one. What about this one? Is it groupable? Sure does look groupable, doesn't it? Remember, though, when you group, I like to make sure that you put this negative inside of there. That helps you factor it out properly. Now let's factor out a GCF of x squared out of the first group, giving me x minus 1. I'm going to factor out a negative number because the first term's negative, 25, and that will flip this sign, making it -1 as well. Got a common factor of x minus 1. We'll factor it out. And so this factors as x minus 1 times x minus 5, x plus 5. So our solutions are 1, 5, and -5. Okay, let's go to the last one. Does not look very groupable, but at least the number in front of the x cubed is a 1, right? So our possible rational roots are plus or minus 1, plus or minus 2. Let's see, does 3 go into it? Yeah, it does. What about 4? Yeah. 6 does. 9 does.
Wow, I forgot a lot of numbers.
12 does. 18 does, and 36. Now, most likely, the numbers that are going to go into it will be over here, right? All right. I was not able to eyeball the last one, so give me a chance to redeem myself here. Okay. All right, I'm going to try -1. Huzzah. So I can now factor this as x plus 1. Remember, that's the 0, and it's the opposite of the factor there. And then this becomes x squared minus 12x plus 36. Is there anything that multiplies to 36 and adds to 12? Well, this actually looks like a perfect square trinomial to me. This is x minus 6 squared. Because it's x minus 6 times x minus 6. So our solutions are -1 and +6. All right, as an exit ticket, I'd like you to maybe just kind of connect this back to what we learned. Can you write a cubic function that has x-intercepts of -3, 2, and 4? And that's it for this lesson.